Last class, we were talking about simple gas laws. We talked about Boyle's law, we talked about Charles' law, we talked about Avogadro's law. Those all relate two different variables. Boyle's law is pressure and volume. So the example of that is like squeezing a basketball or cranking down on one of those cheap water bottles to get the pressure to increase so that you can shoot the lid off into the air when you eventually flick the lid off. Charles' law is the one that relates volume and temperature. And then the last law that we talked about, Avogadro's law, is basically just what happens when you blow air into a balloon. It gets bigger, or inflate a tire. It's the law that has to do with all those things. It's the one that has moles in it, and Avogadro, of course, we know for having moles. The unit, not the facial or body feature. Fortunately for us, there's an easy way to combine all of those gas laws together, and that is the ideal gas law. So I was kind of teasing that we would get to the ideal gas law. So we can cram all of these relationships that we've talked about into one law to rule them all. And that law is PV equals nRT. This is one that you should memorize, especially if you're okay with doing a little bit of math, a little bit of algebra, a little bit of rearranging. PV equals nRT will let you get any of the other gas laws. It'll also let you get gas laws that we didn't talk about. So you can come up with the combined gas law, you can come up with the Gay-Lussac gas law, and there might be one more that I'm forgetting. All the gas laws, though, you can get, all the simple gas laws you can get with PV equals nRT. P being pressure, V being volume, N's the number of moles, T is our temperature. Remember that temperature is in Kelvin. For gases, temperature is always in Kelvin, so make sure that your temperature is in Kelvin or you will get the wrong answer. And then R is our ideal gas constant. We are often going to be using this R value. However, there are other versions of the ideal gas law constant that have different units. One of the nice things about having R is that it tells you what units everything else needs to be. So we've got liters, that means our volume is going to be in liters. It's got atmospheres, that means our pressure is going to be in atmospheres. Moles is always going to be moles, K, Kelvin is always going to be Kelvin. But you could possibly find a version that was liters and bar, or liters and PSI, whatever crazy units you want to come up with. There's probably an R version for that. You can find it, I'm sure, on the Wikipedia page for the ideal gas constant. We are typically going to be using this value. Sometimes you'll see this rounded off. You can also find versions with more significant figures if you're really concerned about your significant figures being limited by your ideal gas constant. Okay, so here is how we can come up with our other gas laws. You may remember that I talked about this fish-shaped sign, this fish or alpha-looking symbol that means is proportional to. And I said that that is proportional to means equals with a constant in there. And we can see that if we take PV equals nRT, and we have constant number of moles, constant temperature, so the things that would change are P and V, we get an inverse relationship between pressure and volume. So we divide both sides by P to get P underneath nRT. If N, R, and T are all constant, V is equal to whatever this equals divided by P. We can make that a proportionality and get rid of the constant sign. And now we've got V is proportional to 1 over pressure, which is Boyle's law. Or the way that we would have likely memorized it, if you chose to memorize it, we want to relate pressure and volume. We leave pressure and volume on the same side, and then we just copy paste it. We say that one side is 1, the other side is 2, and now we've got our Boyle's law. Charles' law relates volume and temperature. So if we take PV equals nRT, and we do a little bit of rearranging, to get volume and temperature on the same side, we get V over T equals NR over P. We say that NR over P is constant, so we copy paste our V over T. We say that this side is 1. We say that this other side is 2. We cut out the middleman. V1 over T1 equals V2 over T2. So as long as you know the labels for the two things that you're trying to relate, or the three things potentially that you're trying to relate with your simple gas laws, you can make the simple gas law just by rearranging PV equals nRT. Just get all the stuff that you want on one side. Everything else that's not changing goes on the other side. You copy paste the side that you care about. Boom, you've got your simple gas law. It doesn't help you with remembering that they're named Boyle's law, Charles' law, Avogadro's law, Gay-Lussac law, combined gas law, etc. But it'll let you do the problem. And I think that's more important than remembering some old dead guy's name. Any questions about any of that? The other cool thing about the ideal gas law is that it lets us work with one single state. So we don't have to have two sets of variables like we have with all of our simple gas laws. For example, we've got a tire, and not just our clothes, but something we can drive on. So we've got an 8.5 liter tire. It contains a certain amount of gas, and we also know the temperature of that gas. We want to know what's the pressure of the gas in the tire. We don't have a pressure pump, but for some reason we know the volume and the number of moles. So we can roughly estimate what's the pressure of the tire. We can figure it out in atmospheres and PSI. The one thing that's not so nice about the ideal gas law is that R has a lot of units. That's the one thing that I will say is not so nice about doing these problems, is that if we're doing our due diligence, we're writing in a lot of units. But that's really just a minor annoyance. It's not really a hurdle or a problem. Okay, so using our R value written there with liters, atmospheres per mole Kelvin. And we also know that PV equals nRT. We are solving for pressure. To solve for pressure, we want to move volume to the other side so that we get P, pressure, equals nRT over V. nRT over V. And then, in this case, it's as simple as just plug everything in. So we plug in N, which is our number of moles, 0.552 moles, times R, with all of its fun units, and we've got T, and then on the bottom we've got our volume, 8.50 liters. Then we can go through and make sure that everything cancels out correctly. This is just to check to make sure we did our algebra. If we didn't do our algebra correctly to get here, there's a good chance that you would also be in the camp that might, not get the right units out anyway. But we'll do it anyway. So we've got moles, and in the bottom of our units, for our R value, we also have moles. We've got Kelvin down there. We've got Kelvin up here. Kelvin cancels Kelvin. In the top of our units for R, we've got liters, and we've got our volume in the bottom, which has liters. And then the unit that's left is atmospheres. Part of the important part of doing these problems is making sure that we're answering in the correct units. So we want to carry through the pressure value that we didn't get rid of. This will help mitigate some of the solving problem correctly but giving the wrong units and so it's wrong, that we might run into with problems like this. So we're going to multiply everything that's on the top, the 0.5, R, and 305. We'll divide that all by 8.5. And we get a value of 1.625 ... atmospheres. We'll round that for 3 significant figures. So it's 1.63 atmospheres. We also wanted it in PSI. So we're going to multiply by 14.7. There's 14.7 PSI at sea level, roughly. So this would be 23.9 PSI. We're probably a little underinflated. Although it is a big tire, so maybe it's not that big of a tire. I don't know how much air tires hold. It's probably a little low. Any questions? Cool. Another thing that we can do that I'm probably not going to show you, since our R value has all these units in it, we could, if we wanted to, if we needed to, if we didn't remember PV equals nRT, if we forgot PV equals nRT for some reason and we didn't want to rearrange it or something, we can also, there's a dimensional analysis approach where we use the units of R and like, is it on the top or on the bottom to get the final units out correctly. You can figure out what the PV equals nRT is just based on the units. I think that's probably not helpful for most people, but it is an option if you're unit savvy, for example. Here's a more realistic example of an ideal gas law problem. What volume, so we're finding volume because volume is right next to our question word. What does about a half mole of gas occupy at a pressure of 715 millimeters mercury and a temperature of 58 degrees Celsius? This is the other thing that can be a little bit annoying, a little frustrating, a little bit rote about doing ideal gas law problems, is that we often have to convert units. So our R value, 0.08206 liters atmospheres per mole Kelvin, has units of liters, atmospheres, moles, and Kelvin. And so we need to make sure that all of the units that we're using with our R value are in liters, atmospheres, moles, and Kelvin. Our N has units of moles, which is great. It's usually just going to be moles, or we'll convert to moles. Our pressure is in millimeters mercury, so we'll need to convert this to atmospheres. And our temperature is in degrees Celsius, and so we'll have to turn that into Kelvin. So we've got a couple of conversions to do before we can get started with our problem. It might be helpful, some of you might find it helpful to go ahead and write all your variables out on the side. Ultimately, that's up to you. So we have pressure provided, 715 millimeters of mercury, temperature 58 Celsius, number of particles 0.556 moles. And we're solving for the last one, which is V. If we write out our little PV equals nRT, solving for V, we want V by itself. We're going to move P to the other side. So it's nRT over P is what we're going to be doing equation-wise. Before we do that, it would be a good idea to convert our units, otherwise things will get crazy. So converting from 715 millimeters mercury, there are 760 millimeters mercury, the same as torr, in 1 atmosphere. So we're going to divide by 760, and it's 0.9407 ... atmospheres. For temperature, we're going to add 273.15. So 331.15, we would round this to the ones place, Kelvin. The conversions get a lot faster if you have your conversion factors memorized. It can be really quick. The more you do them, the more you'll have them memorized. All right, and then after that, all we have to do is plug stuff into our nRT over P that we figured out earlier. 0.556 moles times 0.08206 liters, atmospheres per mole, also per Kelvin, times our temperature, 331 and some change Kelvin, all over 0.9407 ... atmospheres, checking that our units cancel out. First up, we've got moles and moles. So our moles cancel, perfect. We also have Kelvin up here. Kelvin will cancel Kelvin. And last but not least, we have atmospheres on the bottom from our pressure, which will cancel the atmospheres on the top of our R value units. The units that we get out are liters. We were just asked for a volume, we weren't asked for specific units, and so it's easiest for us to just leave it in liters. So we'll multiply everything that's on the top, divide by our atmospheres on the bottom, and hopefully we get a reasonable answer. We get a value of 16.05 ... liters. We'll go ahead and round that for 3 significant figures. 16.1 liters. Questions? Cool. We could also do something like this. Determine the pressure in millimeters mercury of a given amount of grams sample of helium in a given volume at a specific temperature. So here we're finding pressure. We specifically want millimeters mercury. This is about as much work as you can get into one problem. So we're finding pressure. That means that we have to have our other variables, V, N, and T. Of course, they were given to us in the not the most helpful units. So for volume, we've got 648 milliliters. We'll want to convert that to liters, so we divide by 1,000. 0.648 liters. Our temperature of 32 degrees Celsius turns into 305.15 Kelvin. And I put that in the wrong area. That's fun. Okay, scooch that down. And then for N's usually moles, we've got 0.133 grams helium. So we would need to divide by our molar mass of helium, which is about 4, to turn that into grams, or sorry, moles. So 0.133 divided by 4, 0.03325 moles. We're finding pressure. So from PV equals nRT, divide both sides by V. Pressure is nRT over V. So we plug in the values that we just converted to. Our 0.03 moles times our R value, with all of its units, times our temperature, and divide that all by our volume, 0.648 liters. I'll skip us running through everything that cancels because it cancels. And we'll be given, or we'll end up with, some unit of atmospheres, some amount of atmospheres. So we get 1.284 and change atmospheres. We'll round that to 1.28. Atmospheres, final answer? Not final answer. What units were we asked to provide? Millimeters mercury. So we have to convert to millimeters mercury. Doing a great job at writing. It's 760 millimeters mercury equals 1 atmosphere. So it's 976.5 millimeters mercury. So we'll round it up to 977 millimeters mercury. Question?
Let's say it was like hydrogen gas. You do like for the number of moles calculation, would you do divide by like 2 times 1 grams or 2?
Yeah. So if it was hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, any of our molecular elements or diatomic elements, we would use F2, H2, etc. So it would be, in the case of hydrogen, that you use 2.016 grams per mole, 2 times the molar mass of hydrogen.
And typically like this be like molecular compound.
Yeah, same idea for any of our other polyatomic elements. Other questions? Cool. There's another thing that we can do with our ideal gas law. We can calculate, this is sometimes a helpful quantity to have, we can calculate a molar volume. And the conditions under which we're going to calculate this is called STP, standard temperature and pressure. So S for standard, T for temperature, P for pressure. Our standard pressure is 1 atmosphere. Where is the temperature 1 atmosphere? Pressure 1 atmosphere? On average. What elevation? Sea level. I enjoy going to the beach. It's not my first choice of place to go, but I enjoy going when I'm drug along. I'm always like, boy, I'm glad that I did decide to actually go to the beach with y'all. I like being at the beach. So we're at sea level. Our standard temperature is 0 degrees Celsius. What is 0 degrees Celsius? What's important about that temperature? It's the freezing point of water. I personally don't like being in freezing cold weather. It's not my favorite. It's better than 115 degrees, but not my favorite being at 0 degrees Celsius. If I was in freezing cold weather and I was at the sea, though, that's a nice offset. That's okay. I'm okay with being at the coast. We'll get some clam chowder. So one of the ways that I recommend remembering STP is freezing cold, but at least you're at the beach. Or you could just memorize them as 1 atmosphere and 0 degrees Celsius. They're convenient temperature and pressure. So we can calculate molar volume of a gas at STP, which we'll go ahead and do real quick. So we've got 1 mole of a gas. Our temperature is 273 Kelvin, and our pressure is P, 1 atmosphere, PV equals nRT. So the volume, you don't need to be able to do this calculation, but it could come in handy if you forget the number and you somehow remember STP. So V equals nRT over P, where we've got 1 mole times our ideal gas constant times our temperature, freezing cold, and our pressure of 1 atmosphere. We're at the beach. Our units all cancel out like we've seen before, and our volume should come out to be right around 22.4 liters. So if we're at STP, if we're freezing cold at the beach, 1 mole of any gas has a volume of 22.4 liters. Again, this is an approximation. Another note about this that's, I don't know, maybe relevant, we are roughly at sea level. We're like close-ish to sea level. And even if it's 90 degrees Fahrenheit outside, that's only like 35-ish Celsius, which is not that far above 0 degrees Celsius when we're on the Kelvin scale. So you can use this as like a crude, like back of the envelope sort of calculation if you want to figure out how many moles of a gas you have in some container. You can use this 22.4 liters equals 1 mole as a conversion factor. And it is a very useful conversion factor for gases at STP. It only works for gases at STP. In the like actual calculating when it sort of matters, aka when there's points on the line. The identity of the gas also doesn't matter. That's one of the properties of our ideal gas law, is that the identity doesn't matter. It just matters how many particles, how many molecules, how many moles we have. Also important maybe to note that 1 mole of different gases is going to have different masses. Like helium is going to be 4 grams per mole. If we have F2 fluorine, it's going to be more like 38 grams per mole. So even if we've got the same volume, the density is going to be different. The mass is going to be different. But any gas, whether it's helium, xenon, methane, if it's at STP, if we're freezing cold at the beach, it's going to have this 22.4 liters volume, roughly. And we can use that to do some problems. So assuming ideal behavior, assuming we can use PV equals nRT, our ideal gas law, which of these gas samples has the greatest volume at STP? Think about it. What's going to correlate with greatest volume? What goes along with volume at STP? Yeah, higher moles means higher volume. Because we're at STP, so temperature and pressure are going to be the same in all cases. So what the question is really asking, or one of the things that we could think about for this, greater volume is going to come from greater amount of moles. So which of these samples is going to have the greatest number of moles, the largest mole number? That's going to be related to their molar mass. So these are the molar masses. Argon is 39.95. So we could, if we wanted to, calculate 1 gram is how many moles? It's about half a mole. Half a mole is going to be 11.2 liters of volume. If we move up to oxygen, oxygen's way bigger at almost 32 grams per mole. So we're going to be looking at way less than half a mole. And the same thing for argon. It's going to be way less than half a mole. So the one of these that gives us the largest number of moles is H2. And since it gives the largest number of moles, it's going to give us the largest volume. So those are the conceptual connections that you'd hopefully be making for that problem. We can also calculate density of a gas at STP. You hopefully remember that density is the ratio of mass to volume, ratio meaning we're dividing. So density, mass over volume. The density of a gas is normally given in grams per liter. The mass of 1 mole is the molar mass. The volume of 1 mole is 22.4 liters. And so because our molar mass is grams over moles and our molar volume is 22.4 liters per mole, we've got some fun stuff we can do. So we can take the molar mass over the molar volume, the 22.4 liters per mole, and the grams per mole on the top, and because they're both per mole, the per mole part cancels out. Which is why we can find the density with just the molar mass over the molar volume, the 22.4 liters per mole. So we can calculate densities of helium, 4 grams per mole, and nitrogen, 28.014 grams per mole because it's N2. So for He, it's going to be 4 grams per mole in 22.4 liters. Our density, 0.1785 and change grams per liter. For nitrogen, it's going to be that 28.014 grams divided by 22.4 liters. So it's 1.25 and change grams per liter. You could do this for any other gas that you wanted to. You could do it for methane, ethane, propane, oxygen, some of our other gases that are just around. Argon would also be in there. So to calculate density, if we're at STP, we can use this easy trick, the molar mass over the molar volume. Super fast, super easy, super simple. If we're not at STP, then we can find V from the gas law. So we can find V when not at STP. If you're not given an amount, we can just choose the most convenient numbers, which is typically going to be 1 mole. And we've got this version. If you want to just memorize an equation to solve this one specific type of problem, density equals the pressure of the gas times the molar mass of the gas divided by R, also divided by T. Molar mass is grams per mole, and we would just be choosing 1 mole of gas. If you're not using 1 mole of gas, then the equation doesn't quite work exactly the same. So if you're just like, hey, I wonder what the density of this gas is relative to, whatever, you've got the tools now, you can calculate that. That's something you can solve for if your brain ever wanders that direction. So let's calculate the density of xenon gas at a pressure of 742 millimeters mercury and a temperature of 45 degrees Celsius. Density for gases is typically going to be grams per liter. We can use the identity of the gas, xenon, to get our grams per mole. We were not told specifically that we had a specific amount of moles, so we can just pull our molar mass from the table, our periodic table. So 131.29 grams per mole. If you forgot this equation, we could also just figure it out. But you would need to know that density is mass over volume so that you could pick the correct units to hodgepodge this together. I'm going to assume that we're not going to do that most of the time, so we'll solve it with the equation. It's also just easier. So D equals PM personal message over RT retweet. It's the weird things that stick. Okay, so for PM, we got to convert our pressure from millimeters mercury to atmospheres. So we're going to divide by 760. So 0.976 atmospheres. Our molar mass is 131.29 grams per mole. On the bottom, we've got R, which has all of its fun units along with it. And then temperature, we have to calculate from Celsius. So we'll take our 45 degrees Celsius, add 273.15 to it. We get 318.15 Kelvin. How do our units work out? Presumably nicely, because we use the equation. If we didn't use the equation and we were trying to hodgepodge this together, this is part of why I just didn't bother doing we can put it together by ourselves with just knowing the units, because we've got a whole lot of units. And in my experience, most people just get confused by the units. But let's go through and cancel stuff out. We've got an atmospheres on the top. We've got an atmospheres in our R value that's on the top. So these two cancel out. The one on the top's in the numerator, the one on the bottom's in the denominator. We've also got, on the bottom part of the equation, we've got Kelvin. We've got Kelvin that's like double on the bottom. So secretly, this is on the top. Those will also cancel because they're one's on top, one's on bottom, respectively. And then we've got moles on the bottom, on both the top and the bottom, and those will also cancel out. This moles on the bottom is secretly on the top. This moles on the right is secretly on the bottom. It's so fun. And then the things that are left over are the grams that are on the top, the liters that are on the top of the bottom. So they're both just going to carry through. And then we get to plug in our big numbers, big strong numbers. When we're solving problems, as a reminder, when we're solving problems that have multiple things on the bottom, it's a good idea to put everything that's in the bottom in parentheses so that you don't accidentally multiply by 318 at the end. The density is 4.91 grams per liter after we round, which is a lot higher than helium. It was also a lot higher than the nitrogen that we saw earlier. Questions? I don't really want to do another one, if that's all right with everyone. Come ask me about it later if you really want to know. All right, conceptual question. Arrange the following gases in order of increasing density. So smallest to biggest, or small to big. Density at STP. The gases that we have are neon, chlorine, fluorine, and oxygen. What's going to be something that we can find that's related to density? What's related to density for gases at STP? Molar mass. And how are they related? Is it when one goes up, the other goes up? Is it when one goes up, the other goes down? Yeah, when one goes up, the other goes up. Density is the molar mass over the volume. At STP, it's the 22.4 liters. So if we increase our molar mass, we're also going to increase our density. So what we're actually, one way that we can solve this, is we're arranging these in order of smallest molar mass to biggest molar mass. So we'll have to figure out what are their molar masses. And for questions like this, we can do some approximations, which is awesome. So for neon, we can just pull that off the table. 20.18, that's about 20. For chlorine, chlorine's 35.45 for 1. We've got 2, so it's going to be 70.90 or about 71. For fluorine, fluorine's about 19. We've got 2 of them, so we can just call it 38. For oxygen, 1 oxygen's about 16, so for 2 of them, it's about 32. And then it's a simple matter of pick the smallest number first. So first up is neon. Next up would be our oxygen. Number 3 would be our fluorine. And so our last one would have to be the chlorine. And then we just pick the one that matches. So starting with neon is A. We can also find the molar mass of an unknown volatile liquid. Volatile, in this case, means that it boils at a lower temperature than water. Basically. So things that make your hands cold when you put it on your hands, like hand sanitizer, acetone, some other liquids that you probably shouldn't have on your hands, like gasoline. That's the sort of volatile liquid that we're talking about here. We can figure out that experimentally. So first we would need to heat a weighed sample until it becomes a gas, or we would heat something to make a gas, cool it down, and then weigh the sample. We would also have to know the temperature, the pressure, and the volume. The reason that we need temperature, pressure, and volume is so that we can find N, our number of moles. And since we would have the number of moles and we'd have the mass of the sample, we can calculate the molar mass from mass over moles, M over N. So this would be a way that we could experimentally determine something. I believe we're doing this in a week, unless it's our Thursday lab. I don't remember which one it is, but we're doing this one soon, something like this soon. So you've got that to look forward to. Example of this, we've got a sample of a gas. It's got a mass. It's got a volume. It's got a temperature. It's got a pressure. We want to find the molar mass. And since we've been having so much fun watching me do examples, I figure I'll give you a little chance to work on something yourself. Just scribble down all the variables for you. Okay, so give that a shot. Okay, so to solve this problem, to find molar mass, we need the mass. That's the top part of molar mass, usually in grams. We also need the number of moles in moles. Moles shows up in our PV equals nRT. If we divide both sides by RT and flip the left and the right sides, N equals PV over RT. We do need to do some conversions because we need liters, atmospheres, moles, and Kelvin. We've got liters for our volume. We need Kelvin for our temperature. which is about 361.15 Kelvin. Our pressure, we're going to divide by 760. There's 760 millimeters mercury or torr in 1 atmosphere. So 1.28 and change atmospheres. And now we can go ahead and solve for our number of moles. So we'll take our pressure, 1.28 and change atmospheres, times our volume of 0.270 liters, divide by our R, liters atmospheres per mole Kelvin, and also divided by our temperature. A bunch of units cancel out. The moles is on the bottom, which is the multiplication division equivalent of a double negative. So this will give us moles. You should get 0.01168 and change moles. And then we would also want to convert our milligrams to grams, and then we put in for molar mass. So our molar mass, 0.827 grams divided by 0.0116 and change moles. None of our units cancel out, so we are left with grams per mole. And we get 70 point, I think we'll round this to 3, so 70.8 grams per mole. So this would be a pretty decent approximation of chlorine gas, Cl2. Identifying the gas is just like bonus. Questions? Cool. Something that we could do. This might be similar to how we do something in a lab. I don't know if we do this in our lab here specifically, but other labs might do something like this. So let's say that we have an organic chemist. Our organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask, puts the flask in boiling water that vaporizes the liquid, and because the liquid's being vaporized, it's expanding drastically from its liquid state to its gas state. That forces all of the air out of the flask. She then closes the flask, either by sealing it with foil or some other method, and reweighs it. Since you've sealed the flask, afterwards, now we have the mass of the flask with just the colorless liquid in it. Presumably in this circumstance, we'd also let the air return to the flask. Details. The data is given below. Calculate the molar mass of the liquid. So we've got a bunch of variables. We've got our volume of the flask. We've got the temperature of the boiling water. We've got the pressure in the room. We've got the mass of the flask plus the gas, and the mass of just the flask. We can find the mass of the gas by subtracting the flask plus gas and just the flask. So 78.416 minus just the flask. we've got 0.582 grams of gas. We need to solve PV equals nRT for N. So it's going to be PV over RT. We also need to convert some units. We need to convert from milliliters to liters. We need to convert from degrees Celsius to Kelvin. We need to convert from torr, which is the same as millimeters mercury, to atmospheres. .992 and change atmospheres. Then we can plug into our N equals PV over RT. So we've got pressure and volume on the top, and then we put our R value. And our T value. As we saw earlier, all our units cancel out except for moles. We've got 0.0069 and change moles of gas. And then last but not least, we can calculate our molar mass by taking mass and dividing it by moles. And we get a value of 84.33 and change grams per mole. We would probably round this to 84.3 grams per mole. And I don't know off the top of my head which hydrocarbon that is. Questions? It might be hexene, if my math was correct. All right, so we've been talking primarily about where we've got one gas. There are often times, most of the time, when we will have a mixture of gases, at least two gases together. Most gas samples are mixtures rather than a single pure substance, partly because it's just hard to purify things. But anyway, we'll typically have mixtures of gases, dry air, air with no water in it. So the air that we're breathing, but take the water part out, is mostly nitrogen, oxygen, argon, and carbon dioxide. So the air that we're breathing right now is 78% nitrogen. It's mostly nitrogen. Nitrogen's inert. It's not a big deal. The oxygen's the stuff that we really like. It's also flammable. And then there's a little bit of argon and a little bit of carbon dioxide. It's maybe a little bit higher than that, 0.04%. In some applications, we can think of a gas mixture as one gas. So even though air is a mixture, we can measure pressure, volume, and temperature. As if it was a pure substance, we can use our ideal gas law and get some pretty good approximations of the number of moles of molecules in an air sample. Even though they're different molecules, because they don't really interact with each other, Nitrogen, for example, is really inert. Argon's really inert. Carbon dioxide, really inert. So they're not really interacting with each other probably all that much. Oxygen, also in this context, inert. So even though these gases behave independently, even though they're separate gases and they're all mixed together, we can kind of just treat the whole thing as one mixture, which is really convenient for us. And so if we're in a situation where we can treat all the gases basically as the same gas, where our ideal gas law holds firm, the pressure of a single gas in the mixture can be figured out. The pressure of one gas in a mixture is the partial pressure, not the total pressure, the partial pressure. The pressure of one part, or one component, one piece, one of the chemicals. And when our gases don't really interact very much, we can use Dalton's law of partial pressures. Dalton's law says that the sum of the partial pressures equals the total pressure. So all the gases have their own little component, their own little contribution to the pressure, and they just add up linearly. And you should have Dalton's law of partial pressures memorized. So Dalton's law of partial pressures says that the total pressure, P sub TOTAL, often just P tot, equals the pressure of component A plus the pressure of component B plus the pressure of component C plus however many we have. So if you just have two things, you add the pressure of gas A and the pressure of gas B, that's your total pressure. And now back to this pressure due to a single gas. I'm guessing that we're just getting this from PV equals nRT. So the pressure of a single gas is just going to be the number of moles of that gas times R times the temperature divided by volume. There's probably some other fun math stuff we can do with that, but we will not worry about it. Here's that fun math stuff that we're doing. You don't need to know how to do this. This is just like a math way of basically doing a proof. So from Dalton's law of partial pressures, P total is the total pressure, and the individual gases are PA, PB, PC. So if we write out Dalton's law of partial pressures, and then we substitute in this nRT over V, we can substitute in N, so the number of moles of gas A, times RT over V. We've just separated the N in front so that it's convenient. Since all of these terms that we substituted in for have this RT over V, we can lump those together. So we pull out this RT over V from all of these individual terms, and then we've just got our number of moles adding up. So Na plus Nb plus Nc. And if you add up all the individual number of moles of gases, that would just be the total number of moles of the gases. This is just showing that PV equals nRT is at work here. That's all it is. Again, you don't have to know how to do that. That's just to show you. There are some math nerds in every class, so for the math nerds, there you go. We'll stop after these next two slides. So another thing that we've got that we can work with partial pressure is the ratio of the partial pressure of a single gas to the total pressure is the same as the mole fraction. The mole fraction is just, you can think of it like the decimal of mole percent. I'm forgetting, my brain's so tired. Okay. Mole fraction is this chi sub A. We'll just draw that arrow. Mole fraction. So this is the symbol for chi. I usually put a little, it's not a tail because it's in the front. So chi sub A. So the number of moles of our gas, whatever we care about, divided by the total number of moles. Usually you would see that as a percent. But we can also do it as a fraction, just the decimal form. It should always be less than 1. And we saw earlier that we can transform P to be nRT over V. We've pulled out the RT over V parts for both the pressure total and the pressure of one component. This is just a math way of showing that the number of moles correlates to the pressure. So if we have the mole fraction, we've got know how much moles we have. It's also going to be equal to the total pressure, or related to the total pressure. So we've got this other little interesting bit. I'm going to skip over the math. We'll ignore that for now. The pressure of one component is equal to its mole fraction times the total pressure. So if we've got a mixture 0.25 moles helium, 0.75 moles hydrogen, and that's our entire system. And we've got a total pressure we'll make it 1.5 atmospheres. If we wanted to know what's the partial pressure of the helium, what's the partial pressure of the hydrogen, we can calculate that using our P sub A equals the mole fraction times P total. So for helium, our mole fraction is going to be the number of moles divided by the total number of moles. Our total number of moles, 0.25 plus 0.75, is 1. So chi sub A is equal to 0.25 moles over 1 mole. Very convenient. So our mole fraction is 0.25. Then if we wanted to find the partial pressure, so the pressure from helium, P sub He, it's our mole fraction, 0.25, times the total pressure, which is 1.5. So 0.375 atmospheres. So the pressure contribution of just our helium gas is 0.375 atmospheres. This is the sort of thing that we would do with partial pressure and number of moles and stuff like that. And for gases, oftentimes we'll see it as a percent composition, which is what my brain was trying to find earlier. So for example, nitrogen has 78% composition of air. If you just divide it by 100% to turn it into the decimal form, that's the same as the mole fraction. So it's 0.78 for the mole fraction. If you take that and you multiply it by the approximately 1 atmosphere of air that we're breathing, then the partial pressure of nitrogen gas is about 0.78 atmospheres. So helpful takeaways from this slide, you can turn percents into mole fraction, just divide by 100%. Questions? Great, we'll stop there.